Hello, everybody. Thank you for tuning in. My name is Daniel Birnbaum, and I'm presenting my summer research in particle physics on behalf of Dr. Kate Schulberg, Joshua Queen, and Jane O'Reilly of the Duke University Neutrino Group, as well as a special thank you to the NCSSM Foundation for providing this 5-week opportunity. So, now into my project with a quick contextualization. I'm going to be throwing around the term supernova a lot, so let's quickly get that defined. A supernova is an astrophysical event where a star, like our sun, explodes. And this event is extremely high energy, and there's lots of mass, and there's lots of things that are, as a result of this, that we want to observe. So the significance of supernovas comes from one, the initial explosion, but two, eventually what it leads to. So it can lead to black hole formation, neutron star formation, so on and so forth. Both of those things are phenomena that have yet to be observed very well, yet to be studied very well, and they have potential answers to things that physicists yet know. Another important point about supernovas is that during the explosion, about 70% of the mass of the star is released in the form of neutrinos, and neutrinos are just a tiny, tiny little particle that zip across space at very close to the speed of light. So, one thing to keep in note, when stars explode, they are releasing neutrinos as mass. So, what exactly are we doing? Our project, we are using a technique called coherent elastic neutrino nucleus scattering, which simply means that with those neutrinos that are zipping across space at nearly the speed of light, we are placing nuclei in their way, similar to this nucleus you see in the bottom left corner here, and we're watching as this neutrino hits this nucleus, and we're seeing how far the nucleus is moving, seeing how much that neutrino is affecting it. So, as one would expect, should a local supernova occur with now a great influx of neutrinos, we should see this nucleus move a greater distance. There should be a greater kinematic reaction. And we're hoping to study this and make simulations of this, and so on and so forth. So, the goals of this project is we want to make simulations of supernova events. We want to study the neutrino quantum interactions that come as a result of that kinematic reaction I talked about earlier. So, when neutrinos are flying through the atmosphere, we want to see how they interact with the different nuclei, whether that be deuterium or germanium or sodium iodine crystals, whatever it may be. We want to see how neutrinos are interacting with these different types of nuclei and studying that kinematic and quantum reaction. Using that, we're going to be able to create a baseline data set. Just like I said earlier, we know just about how many neutrinos are entering the atmosphere at any given day, but we want to know how much that's going to increase should a supernova occur in our local galaxy. So how exactly are we going to do that? We are using a device called snow globes, which stands for Supernova Neutrino Observation with Globes. And Globes is a software package that compiles about 15 or 20 years worth of quantum physics and mathematics research, all compiled into about a couple lines of code. And simply, all that we have to do is implement key information about what we're trying to observe. So that's the nucleus type, the size, the weight, the radius of the star we're looking at, how far away it is, the spectral class of the star, etc., etc. And using that, we can simulate all of these events, and we can look at different interactions that would otherwise be extremely hard to detect here on Earth, as these interactions are not very easy to observe. So results, as of this point, they are to be determined. We're 5 weeks in, and this is very difficult and technical work, but we're hoping that the results of this experiment will show that the neutrino flux should be different if a supernova were to occur, and using that, we can make predictions. So what does this imply? So like I said earlier, supernovas result in black holes and neutron stars and things of the like. So we're hoping that with a more accurate way of predicting supernovas, we can then study these things. And studying these things, we hope to, who knows, maybe make a unified theory of quantum physics and maybe even figure out how the universe began. Some future directions. We are hoping that with this more accurate way of predicting supernovas, we can set out a massive alarm to people with telescopes, so people like NASA and other observational groups. We can send out a massive alarm letting them know, hey, there's an influx of neutrinos. Point your telescopes this way, and maybe you'll observe one of the things that I mentioned earlier, that be it black holes, etc., etc. And we're also hoping to implement our technology, the coherent elastic neutrino nucleus scattering techniques, into larger detectors, like the one you see in this bottom left corner here. This is an example of a Super K detector, which is one of the largest neutrino detectors that we have. Thank you, everybody, for listening. I hope this was very insightful, and have a great rest of your day.